This is problem 19 of the QHack 2023 Quantum Coding Challenges, and this one is entitled the Magic 5 Ball. And this problem, what we're being asked to do is to implement the Bernstein-Vazirani algorithm, but instead of using conventional Hadamard gates, we have to use this noisy Hadamard gates. So in this problem, all we really need to do is just code up this circuit that we're given here, and we're already given the function that implements the noisy Hadamard gates. So it's really not that challenging. But I do want to just spend some time looking into the oracle we're giving, this oracle U, because it's given in a form that is slightly different than what you typically see for the Bernstein-Vazirani algorithm. So what is typically given is an oracle that is a black box of this form, where we have some input x and then some auxiliary qubit at the bottom that at the output of this block computes this f of x function, where f of x is the dot product between the input x, so the top qubit, the top register, and this string C, which is what we're trying to figure out, right? We're trying to figure out what this C is. And again, this f of x is the dot product, so each of the components of x and c get multiplied, and then all of them get added up. So if we apply this oracle UF to our input x and 0, right? So the input is the combination of this register x and the auxiliary qubit at the bottom initialized at 0. Then at the output we get on the top x, so here x, and then at the bottom we get f of x, which is the dot product of x and c, right? But in this problem, our oracle looks slightly different. So if we look here, we don't have that bottom qubit giving us this f of x. We're just told that our oracle, when we apply UF on the whole register called x, we get -1 to the f of x on register x. And the reason for this is because typically the Bernstein-Vazirani algorithm is explained using a modular oracle, and what we're giving here is a phase oracle, but we can turn the modular oracle into a phase oracle very easily, and it's very similar to the way it's typically solved. So when we're giving this modular oracle, what we do is that bottom register, that auxiliary register, we initialize it on state minus, right? So we apply an X gate and then a Hadamard gate to initialize it at the minus state here. And then on the top, on this X, what we do is we apply Hadamard gates on every single qubit. And then after applying Hadamard gates here at the output as well and performing a measurement, that would give us the string C. Now, the thing is that this initialization of state minus here in this auxiliary qubit give us exactly what we're given in this problem. So when we do this for the modular oracle, what we get is that at the bottom, it's like not having anything. It's like just having that qubit always at 0. And at the top, it's like having a phase oracle. So basically, the kickback that happens from initializing on state minus allow us to have at the top on just register X an oracle of the form that is given in this problem. So that's all. So what we're giving in this problem is just a box as if we had just what we have here at the top, forgetting about this auxiliary qubit. So we're giving a phase oracle straight up instead of a modular oracle with an auxiliary qubit. So let's go ahead and implement that in PennyLane. So as always, the first thing we do is we import PennyLane and NumPy. And then we are giving this function that just implements the noisy Hadamard gates that we're going to use, and is basically just a depolarizing channel and a Hadamard gate. So depolarizing before and after each of the Hadamards applied. And then here we're given this implementation of the oracle matrix. So all we're doing here is implementing an identity matrix of size 2 to the n, and n here is 5, so that's the total number of qubits. And then we're flipping the face of this diagonal elements, which are basically the values of x here in this equation that when multiplied with the secret string c will give us an f of x equal to 1. So that's all this function is doing here. And then we can go ahead and start coding. So first we define our device, so QML device. But now, since we're using this depolarizing channel that might not generate pure states, what we need to do is use a different device than what we usually use. So usually we do default qubit, but here we're going to use the default mixed device. And we have 5 qubits, and then we define our Q node. And here to this function, we're going to pass this value of lambda, which is a parameter for the depolarizing channel on how it's going to apply the noise. So basically the probability associated with the depolarizing channel. And then all we need to do is, going back to this diagram here, is apply this noisy Hadamard gate for the number of qubits, then the oracle, and then the Hadamard gates again. And then at the end, we're given a code that will compute some expectation value on the poly z's at the output. So we just need to implement a for loop to apply this noisy Hadamard, apply the oracle, and then just repeat this for loop at the output, and then return this expectation value, which is given to us in the problem. And now if we print the output for a lambda of 0.1, for example, we get these values for the expectation values of this poly z's. And if we go here and see that for 0.1, we get the exact same values that we're getting in our output. So that just goes to show that we've implemented this correctly. So I hope this was helpful. Let me know if you have any questions.